Now that we know what LP rounding is, we can get a little bit of a better perspective on it by looking at the geometry. Here we have some integer program, and we're going to call the feasible region of it x. X is a set of lattice points. The linear program relaxation we're going to call P, that is the polyhedron, defined by the constraints. After we've solved the linear program, we used a rounding scheme to get a new solution, x tilde. Now we can see how these three objects are going to relate to one another. We know how we should draw the geometry. X is our set of lattice points. P is this polyhedron that's in pink. We have an objective value in green, and we've drawn the objective value at a constant, so f of x is equal to c along this green line. On this, we can identify our linear program optimal solution. LP opt is where our polyhedron intersects with f of x. The integer program solution is on our lattice point. This is the integer program optimal solution. This is the integer program optimal solution because it's the highest objective value for points inside of our x. When we take our rounding scheme, what we've done is we've taken our linear program optimal solution and we've rounded it to an integer optimal solution. And it could be that we round this solution and we will round it to the integer program optimal solution. But in general, that's not going to be the case. In general, when we take a linear program solution and round it, we'll end up at a feasible lattice point, feasible because our rounding scheme ensures that it's feasible, but this might not be the optimal solution. So this, our rounded solution, x tilde, is going to be on our lattice, and it's going to be inside this polyhedron, but it's not necessarily going to be the optimal solution. We can, however, get an idea of how good this rounded solution is in terms of objective value compared to our integer programming optimal solution. Here we've taken the graph that we've just seen and we've highlighted just the particular points of optimality. That is, we have our linear program optimal solution, our integer program optimal solution, and our rounded solution. And in general, this is going to be the case. We're going to have that our objective function value of our rounded solution is going to be less than or equal to the optimal value of our integer program, and this is going to be less than or equal to the optimal solution of our linear program. And here we should start thinking about our dual bounds. F of x tilde is less than f of x IP because x tilde is a feasible solution. It provides a primal bound on our integer program optimal solution. Our linear program, on the other hand, is greater than or equal to our IP optimal solution because our linear program is a relaxation and it provides a dual bound. Now we can go back to this idea of sandwiching our optimal solution between both a primal and a dual bound to get the quality of our solution. In this case, we have the value of our linear program. We solved it, so we know its objective value. We have the objective value of our rounded solution, and let's suppose that these have a distance of at most epsilon. This is going to imply that the distance between our integer program optimal solution and our rounded solution is at most epsilon. This is why we have these bounds in the first place, to bound the quality of our solution. In this case, in the LP rounding scheme, we happen to have a particular value between our dual bound, our linear program relaxation, and our primal bound, our rounded solution. And this can be attributed to our rounding loss. That is, how much solution value we lose by rounding from a feasible linear program solution to a feasible integer program solution. This should summarize how we should think about rounding schemes for linear programs or linear program rounding. We think of our linear program as our upper bound. We think of our rounded solution as our lower bound. The optimal solution to our integer program is somewhere in the middle. And now we can bound the quality of our solution because we simultaneously have a dual bound, our linear program solution, and a primal bound, the rounded solution, and we can say exactly how far away they are from one another, and therefore how far away our solution is from the integer program optimal.